Morning people, welcome back to the next lesson on cantilever beams, where we're going to work out the support reactions. And of course the support reactions is just revision from what we've done in applied mechanics. And then we're going to draw the shear force diagram and we're going to draw the bending moment diagram, okay, and discuss one or other two things just to see the differences between the cantilever and the simply supported beam. Okay, alright people, the first thing I'm going to do, I'm going to draw in the reactions where I think they are going to be. So let me do this. So there's definitely going to be VA. So VA is going to be sitting, I want to be a straight line. Oh man. Alright, there's my VA. My VA is going to be sitting over there. VA. And then let's call VA, and of course my MA is going to be sitting anti-clockwise because the beam wants to rotate clockwise, so the reaction moment is going to be anti-clockwise. I'm assuming that. And because we have now remember, if it's built in, it will have three possible reactions at the support here: a vertical, a moment, and a horizontal. But because there are no horizontal forces acting, there's no horizontal reaction, so there's no HA. Okay, so HA is 0. Right, let's take moments or find VA. So I'm going to say the sum of the moments about A is equal to 0. Right, so that's going to be a negative moment at A. Negative moment at A is anti-clockwise plus. And as you can see there, all the loads on the beam is going to be clockwise with respect to A. I'm going to do the point loads first. It doesn't matter the order, just take all of them. So it's 48 times 2.2, or 48 times 2.2 plus 51. Oh, that 5 doesn't look so like it, does it? 51 times 4.3. There we go. Plus UDL. That's 21 times 2.2. 21 times 2.2. And you all know by now, that's just the force. We still need to multiply by its lever arm, which acts halfway through the length of the load. So it's 2.2 over 2, which makes it 1.1. Plus 47. And the total value of the UDL is its length multiplied by 3.2 times the distance from the centroid of the center of the length of the load to the point we're taking moments about, and it is 5.90. 5.90. If you're not sure, work it out and see for yourself and check your answer against my answer. Are there any more? There's no more. Is equal to 0. Okay. Right, so therefore the moment at A is equal to 1263.08, and put in the units of measurement. If you leave it out, I take off a mark because I'm feeling in a good mood. And of course then the answer is positive. What does it mean? It means that our assumption that MA is anti-clockwise is in fact correct. Did you get that? Doesn't mean it's positive, it's clockwise. That's going to be wrong. Means that because it's positive, it means that our assumption that MA is anti-clockwise is in fact correct. Okay, right. I'm going to do VA, so I'm going to sum vertical. So I'm going to say the sum of the forces in the vertical is equal to 0. Right. So VA is up, so it's VA. Okay, minus 48. Minus 51 minus 21 times 2.2 minus 21, oh man, 21 times 2.2 minus 47 times 3.2, 47 times 3.2, all of that is equal to 0. Right. So therefore VA, check your answer, and you only proceed until you get the answer the same as mine. Check your answer against mine, and I got 295.60. You should have gotten the same. 295.60 kilonewtons. Kilonewton meters, kilonewtons. It's not the same thing. Yeah? Okay, and because the answer is positive, it means that our assumption that VA is going upward is in fact correct. Okay, so VA is 295.60 kilonewtons, and MA is, I'm going to leave it out for now. Okay, it's just so, let me squeeze it in there. 1263 point, I'm going to just do that over there. Here we go. Okay, right, people, so now we need to draw in the shear force diagram. That's the next part of the question, right? I'm going to draw in my line. Let me just do something quickly here. Just give me a second. Alright, people, I've drawn in my projection lines, okay, where the loads are going to change, and they are vertical and they are parallel. Okay, not any old skew ones. And remember, it's a graph, so to some reasonably good scale. Okay, so there's my shear force diagram. Shear force diagram is over there. Right, so plus at the top, minus at the bottom. That's my zero line. Okay, so what's the shear force at A? It's 295.60. So to some good scale, 295.60. 5.60. Right, so, and it's plus, so it's, I'm going to pick up my calculator, 295.60, and I'm going to say minus 21 times 2.2, minus 21 times 2.2, okay, and I get 249.40, and because it's a UDL, it's a straight inclined line down to B. 294. Did I get it right? I did not get it right. Got the wrong way around, didn't I? It's 249.40. 249.40. I'm going to leave it at O. Right. At B, we've got a downward load of minus 48. So with that same value on my calculator, I say minus 48 is equal to, and I get plus 201.40. What does plus mean? It means plotted that amount above the zero line, so it's 201.40. So it is 201. I don't think I should do it there. So it's 201.4. Right, what's happening between B and C? We've got no UDL, so it's a straight horizontal line from B to C. Right, and it's going straight like so. Okay, and that value is the same throughout. And what's happening at C? We've got a load of minus 51. So with that value on my calculator, I say minus 51 is equal to, and I get 150.40. So it's 150.40. Right, and what's happening from C to D? C to D, I've got a load of minus 47 times 3.2. So with that value on my calculator, I say take away 47 times 3.2, close brackets, and levelly I get 0.00. So I've got a straight inclined line all the way down to there, and it closes perfectly. Okay, it closes perfect. It must go back to zero. You know that by now. Right. Now, if you look at the previous shear force diagrams, okay, they crossed, they went up and down, but what do we see for a cantilever? The shear force diagram is above the cantilever or above the zero line all along the way. Okay, so the area there is positive throughout. The whole area is positive. Okay, so there we have a trapezium. Between B and C we've got a rectangle, and from Z to D we've got a triangle. Right, I'll say that again. Notice there we've got a positive area all the way through above the zero line for cantilever. Right, next part there, we're going to draw the bending moment diagram. Right, so let's put that on over there like so. Maybe I'll make it blue. Alright, people, there I just moved a sketch up a bit, yeah. Just made the drawing slightly smaller. There's the zero run for my bending moment diagram. And of course we know the convention is reserved for bending moment diagram. So at the top is minus, at the bottom is plus. Why? Because in South Africa we plot on the tension side of the beam. Okay. And where's tension gonna be for a cantilever? It's gonna be all the way on the top, because the beam is, if I just drew this in like so, if I could draw the beam in like so, the beam is doing that over there. Okay, the beam is doing this, and if I give it some thickness like so there, okay, and if I did that there, we'll see there that in the cantilever we put steel in all along the top there. Why? Because there's tension all along the top and there's compression all along the bottom. Okay, so we draw on the tension side of the bending moment diagram. Right, let's draw the bending moment diagram. Right, so what's the bending moment? Now, in a regular assembly supported beam, we have the bending moment starting at 0 and ending at 0. But in a cantilever, we have a moment at the fixed end, which happens to be at the left-hand end. Okay, what's the moment there? The moment there is 1263.08. Okay, and it is a negative moment. Okay, it's going anti-clockwise and it's negative, so that means we're going to plot it that amount above the 0 line. So that's plus at minus, so to some good scale, I'm going to draw in like so. So that's going to be 1263.08. Right, and remember that's minus 1263.08. How do we find the moment at the next point? To that negative value we add. Why do we add? Because that's a positive area. To that negative value, because it's a negative moment, we add the positive area of this, of that piece of trapezium over there. Okay, to find the bending moment at this point here, to the negative value, we add the positive area of that trapezium over there. And how do we find the area of a trapezium? It's that side plus that side, so it's 295.60 plus 249.4 added together times distance between the two, which is 2.2. Okay, do the calculation and check that you get the same value that I do. And what did you get? Yes, you should have gotten minus 663.58. Okay, so minus that plus that gives us a smaller value, but still negative, of minus 663.58. And because it's a UDL along there from A to B, we have a, let me change the color, let me make it blue again. Okay, make it blue like so, and that value there is 663.58. Okay, and how do we find the bending moment at the next point? To that negative value we add the area of this piece of rectangle over here. Okay, so it's minus 663.58 plus 249.4 times 2.1. Okay, do the calculation, check it if you get the same as me, and then you proceed. Yeah, I think you picked it up. It's actually, I got the wrong value there. So to find the bending moment at C, I take minus 663.58 plus 201.4 times 2.1. Okay, not the 249, that's wrong. Okay, I'll say that again. To find the bending moment at C, you take minus 663.58 plus, because it's positive area, the area of that rectangle there, which is 201.4 multiplied by 2.1, and you add it together and it gives you a smaller negative value of 240.64. And because from B to C is no load, so it's a straight inclined line down to there like so. Straight inclined line. Maybe I should just do this rather. It's better there. Looks like straight. Okay, here we go. And what's the value there? 240.64. 40.64. Right. And how do I find the bending moment at the next point? To that negative value, I add the positive area of that little piece of triangle over there. Okay, so minus 240.64 plus half 150.4 times the base, which is 3.2, and it should give you very close to 0. Okay, and of course it's a curve down to the bottom like so. Like there we go. Okay, to give you either 0 or very close to 0. Okay, and our bending moment diagram is finished. Okay, and notice there it's all negative. Okay, so what can you see there in the shear force diagram for a cantilever? If it's got only loads at the top there, the shear force diagram is at the top of the 0 line, and the bending moment diagram is at the top of the 0 line. So can you see how different it is from a similarly supported beam? And notice, there are no points of contraflexure. Did you get that? There are no points of contraflexure because the bending moment diagram does not cross the 0 line in any way. We only have points of contraflexure if we have a beam that's hogging and sagging, as in the previous examples. Okay, so people, there's a cantilever. I took moments to find MA, and I've summed the reactions to find VA. If there's no horizontal forces acting, there's no HA. And I drew my shear force diagram, and I algebraically summed areas under the shear force diagram, and I drew the bending moment diagram, and we can see there again, the shear force diagram and the bending moment diagram is on one side of the 0 line only. Okay. Okay, people, and that's a cantilever. I'm going to do another example of a cantilevers, and then that will be the end of the lessons for similarly supported beams. I'll see you in the next video.